Another technique that's gaining importance in the study of emerging contaminants is halogen-specific total organic halogen analysis. Why is that technique needed?
So traditionally with just total organic halogen analysis, TOX analysis they would call it, you would get one number and it would be all of the organic chlorine components, the organic bromine, the organic iodine all together in one gamish, and you couldn't distinguish those. But it's really important to be able to separate those because we're finding from the toxicology studies and even some from the epidemiology studies that it's the brominated and iodinated compounds, DBPs, that are the most toxic. And those are the ones that are suspected in the bladder cancer cases and suspected also in some of the reproductive and developmental effects, early term miscarriage and birth defects and things like that. And so if we could distinguish those aggregate total organic bromine, total organic iodine from the chlorinated stuff, really important because the chlorinated DBPs are not nearly as genotoxic or cytotoxic or carcinogenic as the brominated and the iodinated DBPs are. So, and the beautiful thing about those measures too is that those include not only the DBPs that we know about, the compounds we know about we can measure, but includes the unknowns that we're not able to identify yet. And we know that we're missing about 50% already, 50% of the DBPs. So that's my big quest, is to find what these things are. So if we can have those surrogate measures to get both the known and the unknown, it gives us a better idea and link that with the toxicology to see if those in fact correlate, the TOBR, the TOI, with the toxicology and with the epidemiology in these studies that we're looking at.
Are there other tools that are in your toolbox that we haven't talked about?
One other tool that I'm thinking about and that we're starting to use, Thomas Turnus's group at the BFG, Federal Institute of Hydrology in Germany, has been using for recent years. Something new is looking at using preparatory LC or preparatory LC mass spec to be able to concentrate fractions from a complex mixture that you have, complex environmental mixture. So say you got a tentative identification using LC-MS-MS, maybe using high resolution mass spectrometry also, and you think you know what a transformation product is or a new high molecular weight disinfection byproduct, but you're not sure. You've got, got a tentative assignment. So what you can do is use preparatory LC or LC mass spec and collect up a fraction, that cut of your chromatogram for a long time. Keep collecting up, keep injecting that sample till you have enough for NMR. So my friend Thomas Turnus in Germany has been doing this, combining mass spectrometry with NMR spectroscopy so we can get more idea, more confirmation of what these unknowns are. So it adds another layer of confirmation because it's often difficult, if not impossible, to get a standard, get an authentic standard of these compounds because they're typically high molecular weight transformation products, and it's difficult to synthesize those things and you often can't purchase them. So if you can get another little layer of confirmation, it's good.
So you mentioned earlier that you also have to get standards. And so that's a very difficult thing with emerging contaminants, and you just kind of made allusion to getting samples. So how does that issue figure into your work?
So if at all possible, if it looks like an important compound that I've just identified, a new unknown that no one knew before in drinking water or whatever sample it would be, I try my best to get a standard of it. If I can purchase it from Sigma Aldrich or from some other company, I'll get it, order it. But quite often, you can't buy these things. And so I've worked closely with some synthetic chemists as well through the years and to try to get them synthesized. We could do that as well in my laboratory, but it takes a long time. So we'd have to stop everything we're doing to synthesize these compounds. So I work with other people who do that all the time. And Bruce McCaig at the University of Toronto has been fantastic. I used to work with George Majetic at the University of Georgia as well, and they've made through the years, gosh, probably more than 200 chemicals for me, maybe close to 300. It's amazing. They've been amazing. And so then we can confirm what we've tentatively identified. And even if you have high resolution mass spectrometry, you still only got a tentative identification until you prove it with a standard. So you want to match the mass spectrum, match the retention time with that standard. And then the great thing about it is once I get that standard, as an analytical chemist, I only need a tiny bit for my work, just a tiny bit to make up a dilution and shoot it on my mass spec and match it. But so what I always do is always get extra made for my toxicologist friends like Michael Pleva at University of Illinois, but others at EPA, and I'll always save them some of that and send them some of the standards so they can test it for toxicology. It's perfect. And so then we have both pieces of information.